So I'm going to run through some stuff that I was working on. Um, it's called the Pade Approximation. I learned about it a little while ago, and I decided to try and implement it into some machine learning models. Basically, all a Pade Approximation is similar to a Taylor series where you have a equation, polynomial, and it makes an approximation for what that is, right? So you can see the red dotted line here approximates what tan h is. So it's pretty accurate too in many different cases. So yeah, jumping into it, I have some data here on inflation and interest rates and unemployment rates and other various features. We'll mostly be looking at three here: the lending interest rate, the unemployment rate, and the inflation rate. Due to Pade's proven accuracy in approximating certain this type of data. So first I started by cleaning the data, getting the categorical features, shaping it, removing unwanted features, and assigning my x and my y, so my features and my response. From there, I just did a quick polynomial fit of the responses. So this would be the unemployment rate. So you can see a polynomial fits it pretty well, right? So that's pretty cool and all. So if we go down here, now I apply a Pade approximation to that, you can see it's much more accurate than the polynomial fit, which is by a lot, so which is cool. But you can see after a while it kind of diverges off. So my thought here was to create an activation function where instead of a ReLU or a sigmoid, basically the model's training towards what the Pade approximation of the distribution is of the data, especially one like this where it looks like a polynomial function. So coming down here, instead of using the raw normalized response, the unemployment percentages, I found the cubic splines of them because it really accurately represents how each year the unemployment rate changes. So by converting the normalized rates and then finding the cubic splines, I was able to create a model where I have a Pade activation function, which is just the ratio of polynomials, and you set it equal to the Taylor series expansion. I was able to create a model that uses it as an activation function. It's just a super simple, just LSTM model where I have the activation as the Pade and just a few layers. So from there, I compiled the model and then split up my data, created sequences. So I used the sliding window technique where it would use 4, or maybe I used 5 time steps. Yeah, I used 5 time steps. So it would look at the 5 previous years to make the 6th year's prediction. So it would take the first 5 to make the 6th, and then 2 through 7 to make or 2 through 6 to make the 7th, and then 3 through 7 to make the 8. So it's just sliding through the data. So I created these data sequences, right? Fit the model, pretty standard. And here I plotted the loss. You can see it's pretty low and then it has these massive spikes, but after a while it smoothed out. And I was able to, this data went from like 1972, I think, to 2021. So this is the 2022 data I was able to pull approximately from, the first 2.5 months and on. So there's 5 time steps here. And this is the inflation rate and the lending interest rate. So I reshaped that and use it for my prediction. And here's the predicted normalized spline value. So the way to convert a spline back into a normal value, there's this optimization function that basically takes in all the other splines and does a search to see what spline this would be similar to, essentially. So it's called differential evolution. And once I was able to inverse that, I was able to take the normalized percentage and inverse transform that back from being normalized to a normal number. And it predicted that for 2023, the interest rate would be, or unemployment rate, excuse me, would be 3.67%, which is almost spot on to what it is right now. In July, it was like 3.5, and I think right now it's around 3.8. So for a year total, it's pretty close. So I thought it was really interesting. It's something new I've been kind of working on. Right now it's super simple, but I know it can be applied to many different areas and use cases, not only in economics, but I was reading in physics and in like nuclear research for modeling when the chain reaction happens, since it's like a series and it exponentially grows. Something can be modeled really well with this Pade approximation. And testing it against ReLU, ReLU predicted like 6 or 7% every time I did it. This one was pretty consistent, around 3-4%. Most of the time was 3.67 was the prediction it would make. So yeah, pretty interesting stuff. I would like to get your thoughts on it. So yeah.